Hello friends. So today we are going to discuss 5 questions, and these 5 questions are, you can say, are from a momentum part, but not exactly the conservation momentum, and they can be considered as a variable mass system that we can say in general. So in the first question, we are given a uniform flexible rope of total length B and mass per unit length m lies coiled on a smooth horizontal table. One end of the rope is pulled vertically upward with a constant speed u0. At a certain instant, the lifted end of the rope is at a height a of the table such that a is less than b. Determine the magnitude of the force that must be applied to the rope at that instant. So in this case, we are given that we have a rope and that initially is lying on a table. So let us consider this is the table, and initially the rope is lying something like this. It is coiled on our table, and then we catch hold of one of the ends and start pulling it upward. At a certain time, it is given that the length of the rope that is we have pulled is our A. So this is length A. And the total length of this rope is said to be given as B, and the length which has pulled A, it is said that A is less than B. So this is the condition given to us. So we are given that we are having a rope length B, total length, rope length is given as B, and we are also given mass per unit length, that is m. Mass per unit length is given as m. Therefore, from here we can say that our total mass will be m times b. Okay. And so at this particular moment, when the length of the rope is A above the table, we have to find out the force which we are applying to hold this rope. Okay. And this, as we are going to pull upward, there will be change of the mass of the rope, okay, that we have to consider it. So this is basically a variable mass system. Okay. And in this variable mass system, we have to keep in mind that the rope is moving continuously, or we can say lifted, and therefore our this force relationship we are going to use with respect to momentum, not with respect to the acceleration. Therefore we can say that for a variable mass system, we are going to use the relationship that the summation of the forces will be our rate of change of momentum. Okay, this relationship we are going to use. So let us consider that as per our question, okay, so we can divide this set up into two parts. One is a moving part, that is a moving rope, and other one is a stationary part. Okay, that is a rope is stationary. So we can say at height A, first is our moving rope, and this moving rope we can say that its length is our A. So the mass of this moving rope will be equal to mass in the density mass per unit length and multiply by A. And in the question it is given that it is having a speed of u0. So this is with respect to the moving rope. And then we are also having a stationary rope that is entirely lying on the table. We have a stationary rope which is lying on the table. So its length will be equal to B minus A, because B is the total length of the rope, and its mass will be equal to mass per unit length minus multiply by total length. And its the velocity, because it is lying on the table, so its velocity will be equal to 0. So like I said, we are going to deal this force with respect to momentum. Okay. So it means only this moving part is going to contribute towards the momentum. Okay. Stationary part, there is no contribution towards the momentum. So let us concentrate on calculating the momentum. So you can say the momentum of the rope, and that is our P, and P is our moving mass multiplied by velocity, and the moving mass is our MA. So this comes as M times A and multiplied by V. Here A is not the acceleration, but A is given the length of the rope. Okay, A is the length of the rope, and we are interested in finding out the rate of change of momentum. So we simply derivate it. So we get this as dP by dt will be equal to our velocity is given to us as u0. So we write this as u0, and we get this as our u0 and d of dt mass into the length. And in this case, because it is being lifted, so mass, our length is increasing. Okay. Therefore, we can say that our dA of dt will be giving us its velocity. Okay. So we get that dP by dt will be equal to m u0 square. So this is the rate of change of momentum. And now we are going to find out the forces acting on the rope. Forces acting on the rope. Okay. So first force will be the force that is we are holding the rope and pulling it upward. So we are going to call this as a hand force. So we are having upward force, which is nothing but holding by the hand. So we are going to call this as hand force, and that is our F. Then we are having downward force, and downward force is our weight of the lifted rope. Weight of lifted suppose that is given as W, and W is equal to total mass of the lifted rope, that is MA multiplied by G. Okay. And therefore we simply equate this formula. Okay. Summation of forces is equal to rate of change of momentum. Therefore we can say that our summation of forces is equal to rate of change of momentum. And we have two forces, F is upward, weight is downward. Therefore we can write that our F minus MAG is equal to M U naught square. And from here we can write that the force which we are applying in upward direction is equal to our M, we can take as common. So this comes as our AG plus U naught square. Okay, and we have to keep in mind that this is when the rope we have raised above the table is less than the total length of the rope. Okay, this is our first question. Okay. So in the variable mass system, one of the important formula is that the force which we are going to calculate will be based on the rate of change of the momentum. That we have to keep in mind. Second question. It states that a uniform heavy chain of mass per unit length lambda hangs vertically with its lower end just touching the smooth horizontal table. The upper end of the chain is released from rest, allowing the chain to fall onto the table. After the chain has fallen through a vertical distance x, determine the force exerted by the chain on the table at that instant. Okay. So in this case, the chain is falling from a certain height, okay, and after it has fallen through a distance x, it means the x amount of the chain is lying on the table. Okay. So we are going to find out its the force exerting on the table. And so we are given that so we can just draw an approximate figure also. Okay. Initially we are having the chain which is just touching the table. Okay, let us suppose the upper end is point P, and then it is released. Obviously it is going to fall in the downward direction, and after some time it suppose comes like this. Okay, this is only representation to show that we have the x amount of the chain lying on the table. Okay. And this is the upper end of our P. Okay. So we have to find out the force because of this chain, which is our length of the chain, that is x, lying on the table. So let us consider, okay, in this case we are going to assume that our downward we have taken it as a positive. And we are going to write some equations, that is our kinematics equation, but with respect to the falling chain. Yeah. So you can say kinematics of falling chain. Okay. And the chain is will be in free fall, so it means G is going to our acceleration due to gravity, and it is going to start from rest. Okay. And when we can say when the chain length on the table is x, suppose at that particular moment its velocity is v. Okay. So we can say at P it's having a velocity of v. Okay. And so therefore we can say after falling x, its speed is equal to v, and that will be equal to over 2gx. Okay, because it is going to start from initial velocity will be equal to 0. Okay. And now we are interested in the we are once again going to divide the parts on the chain, that is chain that is resting on the table and chain that is still falling. Okay. We have to remember that. So we are going to divide in two parts. You can say parts of the chain, and parts of the chain so we are going to divide it into parts of the chain, and first will be our chain that is rest on the table. So first part is our chain at rest on the table, and we know that the chain that is resting on the table, it is having a length of our x, and its mass will be our mass per unit length lambda times total length, and its velocity will be equal to 0. And our second part will be chain still falling. So chain still falling, that is length is the remaining portion. We are not interested in this remaining portion, so length is not required as such. So we can say simply our length is our remaining portion, and velocity, that is our v we just calculated, is our square root of 2gx. Okay. And once again we are going to use the formula summation of the forces is equal to rate of change of momentum. Okay. So we are interested in the formula summation of the forces is equal to rate of change of momentum. Okay. So we are interested in the forces exerted on the table. You can say our forces exerted on the table, and this we can divide into two parts. First will be the weight of the chain that is already lying on the table, and the second one is the force needed to stop from the upcoming chain. Okay, that's the chain that is supposed to fall. That's we already have the two parts, rest and still falling. Okay, so accordingly we are going to have two forces. So you can say that our first force is equal to weight of chain already in the table. So you can say the weight of chain on the table. And let us call this as weight as our W, and that will be equal to our lambda times x multiplied by g. Next will be our second will be our the force that is required to stop the incoming chain, or in the shorter version we also can call it as a momentum flux. The second will be our force needed to stop incoming falling chain, and we can also call this a momentum flux. Or in equivalent terms, we can also say it as a mass flow rate onto the table. Mass flow rate onto the table. So this will be equal to our dm by dt, which will be equal to our lambda times v. Now we can find out momentum change per unit time. Momentum change per unit time. We can call this as F momentum, which will be equal to our dm by dt multiply velocity v, and dm by dt we just calculated, so this comes as our lambda v square, and v square, v already we know is our square root of 2g. So we substitute it here and we get that our F momentum will be equal to our, this comes as our v square is our 2gx. So it comes as our 2 lambda gx. So therefore we can say total force of the table. Total force on the table, and total force will be the contribution of the both, that is our F is equal to our F, that is our, let me call this as F weight, okay, Fw plus F momentum. And we substitute them, so we get that F is equal to Fw is our lambda gx, and this comes as a 2 lambda gx, giving us that the F will be equal to over 3 lambda gx. So this is the total force that will be because of the chain on the table. Okay. Now sometimes, because this force is dependent upon the x, we can also write it as a function of x. F of x is equal to 3 lambda gx. This is the other way of writing the answer. Come to the third question. So in this third question, we are given that a uniform rope of length of total mass m, length L, hangs vertically in a uniform gravitational field G, with its lower end just touching the horizontal surface. The rope is released from rest and falls limply onto the surface, coming to the rest without bouncing. Determine the force Ft exerted by the rope on the surface as a function of time. At what time does F of t attain its maximum value? Find the magnitude of this maximum force. So the major difference between this and the previous question is, in the previous question we only said that only the partially the chain is on the table, and in this particular question the entire chain is on the table. So this is a major difference between the two. And in this case we are also going to find out two additional things. that the maximum value and the we are going to find the time and the magnitude of the maximum value. Okay, so these are two additional things which we are going to find out. So we are given that we have a rope length that is of L, and rope mass is total rope mass is given as capital M. So we have a rope mass that is given as capital M. So from here we are going to find out its linear mass density. So we can say linear mass density, or also we can say mass per unit length, linear mass density. Suppose that is lambda, that will be equal to total mass divided by total length. And it is given that at the start the bottom end is just touching the table. Okay. And here we are also going to take in the downward direction, we are going to take as a positive part. Okay. This is going to help us to solve the question. And first we are going to discuss the kinematics of the falling rope, in which we are going to use the basic formula of the kinematics. Kinematics of falling rope, and it will be in a free fall, and initially it was at rest. Therefore we can say kinematics of falling rope at time t. At a certain time t, we can write that the speed of falling rope, if at this time t, suppose that is given as v, it is going to start from the rest. So we can say v will be equal to our gt, and length of the rope at this particular moment time t, let us suppose that is our x. So you can say the length of the rope that has reached the surface at a certain time t. Let us suppose we call this as x of t, which will be in this case half gt square. And the rope will finish falling when this value of x is equal to the total length of the rope. So we can write that the rope finishes falling when x is equal to L. So in this case, when x is equal to L, we can find out the time it takes to reach the end. So you can say our time end will be equal to our 2L upon G and its square root. Okay, using this equation, we substitute this x is equal to L, and then we get the time t. And now once again we are going to the contribution of the forces on the surface. So we can say that force on the surface, forces on to the surface. Okay, so first will be our weight of the rope that is already on the surface, and the second will be the incoming rope, which we also called as a momentum flux in the previous question. So we divide into two parts. In the first part we have the weight of the rope that is already at rest on the surface. Weight of the rope already at rest on the surface. Okay. And for this we know that the length of the rope which is already on the rest on the surface is our x. Its mass will be equal to the linear mass density times x. Therefore we can find out that the force because of the weight will be equal to our lambda g x. And we can write the second is the momentum loss of incoming rope. Momentum loss of incoming rope, which we also called as a momentum flux. And so this we can write it as our momentum flux is our dm by dt, which will be nothing but lambda times v, where v is the velocity with which the rope is traveling, moving toward the table. And based on this we can find out the momentum change per unit time. Per unit time, or we can say force because of the momentum is equal to our dm by dt times v. So dm by dt is our lambda v, so this comes as lambda v square. So the total force on the surface on the surface, suppose that is our f of t, which will be equal to our this force because of the momentum and force because of the weight. So you can say Fw plus F momentum. So we substitute them, we get our f of t will be equal to lambda gx plus lambda times v square. And x we already know is our half gt square, and v also know is our gt. So we substitute them, we get lambda g, and this comes as our half g t square plus lambda, and v is our gt, so this comes our g square t square. And we can solve it further. So this will be giving us 1 by 2 lambda g square t square, and this is equal to lambda g square t square, which will be giving us that our f of t is equal to 3 by 2 lambda g square t square. And we know that of lambda, that is a mass per unit length, is m upon L. So we substitute it, we get our f of t is equal to this is our 3 by 2, and we have our mass, sorry, not lambda now, mass g square t square upon L. So this is the force, which is basically a function of time. Okay. And next we have to find out the maximum value of the the time when the force is maximum. Okay. So you can say time when force is maximum. Okay. And from this equation we can say that our f of t is proportional to square of the time. Okay. And we said that our this time is finishes when t end is equal to 2L upon G. Okay. So it means that from here we can say that our T max, that's the maximum time, will be equal to over 2L upon G and its square root. Okay. And we can find out our maximum force. So we can say our maximum force, which is suppose our F max. We simply substitute value of T in the equation. So we get this as our 3/2 m square G square L, and this comes as about 2L upon G. Here square goes by G, L goes by L, 2/2. Therefore we get that the maximum value of the force will be equal to 3 mg. So these were the three parameters we were supposed to find out. First is our force at any time t, then the maximum when the time when the force is maximum, and the maximum value of the force. Next question. Okay. So in this question we are given that a uniform rope of total mass m and length L is initially held in the configuration as shown in the figure. One end attached to a fixed support. Assume that negligible length of the rope initially hangs below the support. Figure I'll draw later on. At time t is equal to 0, the rope is released and allowed to fall freely under the gravity. Determine the force exerted by the support on the rope as a function of time. So in this case, suppose this is a support and we have a rope, and this rope is tied to this support, okay, something like this, and it is given that this length which is below the surface is negligible, okay, only small amount is there, so we can just neglect it with respect to the entire length. Therefore we can say that the entire length is just above the table at this particular instant. Okay, so this is the basic question, and we are going to find out the force exerted by the support on the table as a function of